give a talk here about our research on self-avoiding fractional Brownian motion. As you see in the first slide, it's a collaboration with many co-authors. So it's Chinky Bonales, Cassandra Cabarruc from Philippines, and then Samuel Alterio, and Maria João Oliveira from Lisbon, and Torben Fattler and Martin Krotos from Kaiserslautern, and Luis da Silva from Madeira, who is also virtually here, and Ludwig Streit, who is in Madeira, Philippines, and anywhere in the world. People who know him, he's quite active still. So what I wanted to discuss today is actually about the stochastic quantization of the fractional Edwards measure. That's a more analytic approach to that, what we do. We also do some numerics, which are considering more the scaling of this process. But here I want to go a bit more in detail on the analysis that we are right now doing. So in a nutshell, what happens is, so just think about, you have a random walks from a touristic site. Yeah. So let's say you are in Manhattan and you just walk, and you just go stubbornly one way. So it's clear that the average distance you have from your hotel will be proportional to your walking time, right? So if you assume constant speed, then you don't get tired, of course. So if you are aimless and get drunk, let's say, and then you get randomly turn at every corner, it's clear that the average distance will be square root of t, or proportional to square root of t. This is Einstein, is absolutely clear. And if you are a bit more, let's say, putting attention on where you actually are, and you say that you don't go one edge twice, then you end up with something like a average distance, with people would say is t to the power 3/4, which is still not completely proven. So there are some proofs by Wendell and Werner, but there are still some things open, like self-similarity properties and stuff like that. So, and we want to see what we can do in this question. Yeah. So that means we are taking a look at self-avoiding fractional Brownian motion, or self-avoiding walks. Yeah. The motivation of it is actually coming from polymer physics. There you have a Brownian model generally, and you ask yourself, what is the swelling of a polymer, which is very important for the material properties. And so you check if this head to tail distance, and you want to know how big this is. And the Brownian model would be exactly this number of monomers, small units you have inside of your polymer to the power 1/2. But of course, if you take into account that not two monomers can be at the same point, you have the swelling effect. So you will get an exponent, which we call the Flory exponent, which is larger than 1/2. The question is, what is it? And all of that somehow motivates to look at self-avoiding Brownian motion, self-avoiding fractional Brownian motion. So of course, you cannot just plug in a Brownian model. You have to do a bit more. So in generally, what you do is you take the self-crossings and you penalize them by Boltzmann factor. And this leads then to the so-called Edwards measure. That's what we see here. So you just have here the integral over Donskis delta function. So what this gives actually the integral e to the power minus g times, they call this the self-intersection local time. And this Boltzmann factor actually tells you then that you get something like a weakly self-avoiding path. So of course you allow somehow self-crossings, but asymptotically not anymore. Yeah, for large scaling. But of course it's not strictly like you really don't cross your path. Yeah, just penalize them. That's why we call it weakly self-avoiding. So in the self-intersection local time, so if you look at that, this is already a very analytically challenging object. So you have here the Dirac delta usually. So you can take here a heat kernel approximation, for example. That's what the epsilon means here. And then you can show that in dimension d equal to 1 for the Brownian motion, you converge in L2. And for dimension 2, you have to center your local time, which is of course a small catastrophe for our Boltzmann factor, because then before we had something like a positive random variable, right? Now we have a centered random variable, so it could be that we have some explosions and we have to check if all of this is still true and still working. If we can still put it there as a Boltzmann factor or as a density, let's say generalized density in front of it. And what you see for dimension larger than 3, you have here a conversion of the centered local time in law, where you have here some renormalization factor. For the talk I want to do here, we will just actually discuss these 2 cases later on, or the corresponding cases in the fractional case, which come on the next slide. So we don't go too much in detail here. So how does the case now look in the fractional, for the fractional Brownian motion, and why actually we are doing it? So there is a very nice elaborated paper by Hu and Nuala from 2005 in Annals of Probability, which is actually try to cook down this, or try to establish these results from the papers we have seen before, from the Brownian case to the fractional case. And for HD less than 1, we have actually really that also here the L epsilon converges to L, the positive random variable L in L2. So you have immediately that e to the power minus GL is well defined. So HD less than 1 corresponds to the case when you go back, D equal to 1. Okay. And for HD between 1 and 3.5, we have to center the local time, and then we are still having a centered local time converging in L2. And for the larger ones, as we have seen before, we need some renormalization, and it's a bit more complicated. So the question is, why are we going to fractional Brownian motion? Now, first of all, there are also some other scaling properties, or in the polymers, so motivated from there. You can talk about polyelectrolytes or something like this and try to look at the better scaling behavior there. But you also can think about the analytic point of view. Sometimes it's easier to go a detour to prove something nice. So we will see that for the HD equal to 1/2, for the Brownian case, that means for the planar Brownian motion, that's what I showed at the beginning as a motivation. We want to get, there's not everything is proved, yeah. And we want to get somehow the foot in the door here and make a small detour by the fractional Brownian motion. We're still work in progress. So what about the Edwards measure in the fractional case? Well, there is a paper by Grothaus, Oliveira, Silva, and Streit from 2011, which show that this is a bona fide, well-defined random variable for HD equal to 1 when you have sufficiently small coupling constants. So the T and the G, they are somehow playing against each other, right? So you can make, if the time is small enough, you can make the coupling constant a bit bigger, but they have some properties on G and T. If they are not, so if this G is not too big, then this one is an L2 random variable. So this is absolutely fine. And you actually even have this convergence makes sense. Okay, so this is a well-defined object. And so what we want to do is we want to stochastic quantize this. So we want to find a Markov process which has the Edwards measure is an invariant measure. So what are we looking at is we have a 2D polymer measure. So here you have that's what we are considering. Yeah. Here at the moment we have the Wiener measure. We will take later on the fractional the measure of respect to fractional Brownian motion, and here we have our Boltzmann factor from before. This one is of course the normalization constant. So this is what we call the 2-dimensional polymer measure. L is self-intersection local time, and the stochastic quantization, that means to find a Markov process which has this measure as invariant measure, has been done already by Abeberio, Röckner, Hu, and Su. With the methods of Dirichlet forms, and what they have actually is they use quasi-translation invariance, because what we will see is that we don't have something like we have a problem with Meyer-Watanabe differentiability in the case HD equal to 1 of this particular local time, and therefore you have to come just to a very abstract result. So you know there exists a Markov process. You know that, yeah, because the Dirichlet form technique, you can take just the chapter 4 in the book of Röckner, and then you can just do the whole procedure and everything works, but you don't get it explicit. Yeah? So if you want to have the corresponding stochastic differential equation, and if, for example, you want to do something with it, so you want to do numerics or something like that, it's not working on that paper. So we tried now to approximate this by the fractional case. So what do we know? So we do know that the 7th intersection local time, which is of course crucial because we have it in the exponential function, so let's say generalized potential here. The 7th intersection local time of fractional Brownian motion is Meyer-Watanabe differentiable if h is fulfilling this bound. D is here the dimension. So for HD equal to 1, when HD less than 1, exactly HD less than 1, it's fine. For the what you can see is that for the, for example, a result by Imkeller et al. That for the case h equal to 1/2 and the planar case, that means d equal to 2, we have exactly that L is not Meyer-Watanabe differentiable. That's why there is this problem of Röckner paper, that you cannot use real like integration by parts. So you don't know too much about the generator, you just have a very abstract result. So we have this in the case where HD is less than 1. Okay, so in the case HD less than 1, we have this Meyer-Watanabe differentiability. So if we want to do something with Dirichlet forms later on, this is good news. So we can work with the generator maybe. We can use integration by parts. So what is the goal? The goal is to show the existence of a diffusion process whose invariant measure is the fractional polymer measure. Yeah? So we call this mu GH, yeah? For DH less than 1. And I want to describe this Markov process via the corresponding stochastic differential equation, and then I will tell on one slide that actually we have something like the convergence in the sense of Moscow, most likely. We are not completely finished with the proof, but that's what we want to have at the end of the day. Okay, so what we are doing, I mean, those people you have seen on the co-authors are very much working in white noise analysis. So we want to we worked the whole thing up in the Dirichlet forms and white noise. So you start actually just by putting a setting which spaces you're working on. So we want to have a starting point. So we take just the span of the indicator functions which start in 0 to tau. And we set actually the inner product of two of these indicator functions, the covariance of fractional Brownian motion of BTH and SH. Yeah. So if you have that, then you can of course go to the span of this indicator functions, so the simple functions, and you define this inner product, and then you just make abstract completion and you come to a Hilbert space. So by that, you have induced yourself a Hilbert space, which having an inner product which is related directly to the covariance of fractional Brownian motion is actually doing exactly that what you want, as you know it maybe from the white noise setting. Then we want to construct corresponding generalized functions and test functions. So we take a standard abstract accountable Hilbert space. So what we take is a sequence of eigenvalues which is larger than 1, such that 1 over the lambda k squared here is summable. And then we just define this operator AF on a complete orthonormal system eta k, because we are in a Hilbert space, we have that defined as this one. So we just have here a diagonalization of A along this orthonormal system. And then we can get this HP space as powers of this operator applied to f, where f is an h, and take this h norm should be finite. And afterwards, you just say that the nuclear space, which comes out at the end of the day, is the projective limit of all of these HB spaces. So we are actually exactly like in the construction of the standard Schwarz space, just that we use somehow an adapted construction for our functions. N is countably Hilbert space, Frechy and nuclear. Yeah. Now, of course, you can go to the corresponding dual space, and by Bochner-Sazonov theorem, you can define this Gaussian measure UH by this one. So you just have now actually defined your fractional white noise measure, as you would do it in a white noise analysis. This measure has full support. It's one property, we have a probability space where you take a sigma algebra of cylinder sets. So actually, we get now for every Hurst parameter, we get an L2 space. Yeah. So and to make the analysis, we actually need to define the gradient on a dense subspace. So what we do is we go to the polynomials. So not to break our heads too much, just think about to take this polynomial, so all L2 functions such that I can rewrite it like this, where you have f is smooth. That means this from the complexified test function space here. This is the space of smooth polynomials, and on these smooth polynomials, I can of course define a derivative in direction of eta k, as we do it in the standard case, right? So if you have some tensor power, we take tensor power n minus 1, tensor power n, take the n in front of, take here eta k and make a dual pairing with f, the nth tensor power of f. So if I now take the whole complete orthonormal system eta k, then I have this actually to be the gradient. Yeah? So I have my infinite dimensional gradient structure. And what we see immediately is that the gradient and also this d eta k is defined on the polynomials, which are, of course, dense subspace of L2. So we store in Weierstraße. So then, of course, it's important to consider also the adjoint later on, because we want to talk about Dirichlet form, so we want to talk about integration by parts. For the adjoint, it's actually a standard theorem by Potthoff from 2000. In this paper on differential operators and white noise analysis, the adjoint always looks like this. So you have actually here, if you have the adjoint to the derivative direction of u, we get here the a monomial minus then the gradient. So, and of course, you see that this guy is defined also on a dense subspace. Yeah, for example, the polynomials. So especially what we have then is that the adjoint D is well defined and defined on a dense subspace. So what you have is that the bilinear form here, that means you take the expectation e to the power minus gl of gradient u gradient v, u, v, and p is then directly giving a rise to a densely defined closable symmetric Dirichlet form. Yeah? So we then get at the end of the day a Dirichlet form. Crucial to show that is really Weyer-Watanabe differentiability, because if you take an integration by parts here, you will have the gradient of L popping out, and therefore you need that the gradient of L makes sense. But that's what we have seen. If we are in the case which we are here, that means HD less than 1, we can use the result previously we have seen from who that this one is indeed, L is indeed for HD less than 1 Weyer-Watanabe differentiable. So this makes completely sense. And moreover, you have a generator. Now you can write down the generator directly. So what you get in front is, of course, the number operator, which is nothing else but the Laplacian in the setting, of course. And here you get, yeah, the standard drift, where this one is the 7th section local time. So now we have a generator, and we have much more knowledge than it was in the case of Alberverio and Röckner. Yeah. So and company. So what we what we have is we can now try to really construct based on the generator our process and check what we can do with it. So actually what you get is this Fukushima decomposition, and it's just nothing very surprising, right? So you have a generator, and we know if you just take L as a standard potential, we know how the differential equation would look like. What is a bit strange is actually that you have here a Brownian motion. So you see this process is actually nothing else but the process of the noise of the corresponding polymer path. Yeah, so you would integrate this from, so you have to really integrate this along the monomass. This T here is the compute time. It's not it's not something like this, what we have seen before. It's not the time of the Brownian motion. This is some of the fractional Brownian motion, which is behind the whole story. This is really like a compute time. And so the starting point is some omega and n prime. So you have an n prime valued process. Yeah, I mean, this is the noise of the polymer process, so it's n prime valued. You have here plus square root of 2. This is the a FT Brownian motion on n prime. And then you have this drift here, actually. Yeah, and this is all like this is well defined. So and you have now also a hand on that, so you could actually try to discretize it and also do numerics with it, which is still to come. So we have some preliminary results, but we are still working on that. But what you have more is that one, namely, you see, in the case HD equal to 1, that means the Brownian case dimension 2, we didn't really have this generator, and we didn't really have the SPD or SD. So what we have now, actually, almost, there are still some small details to check, but almost, is that you take a sequence of first parameters, and they correspond to some sequence of Dirichlet forms. And you have actually that you can approximate the case HD equal to 1 for the planar Brownian motion in the sense of Moscow by Dirichlet forms from the case HD less than 1, which means you have all the analysis or all analytic results directly via the Moscow convergence, which we wanted to have. Okay, it's still some things to prove, especially yeah, we have convergence along the chain of Hilbert spaces. There are some technical proofs actually, and you have to show some density relations, but actually we are quite sure that it works, but there are still some things to do. That's why I wrote here in red conjecture. Okay, and that's all for today. Thank you very much.
So thank you very much for the speaker, and I hope you can hear us. Can you? Perfect. Yeah. So we have time for questions and comments, and maybe you can be the moderator and the question number 1.
For the virtual participants, I request to raise your hands. Meanwhile, I'll take questions in person.
Since there is no danger that I infect the microphone, I take off the mask so people can hear me better, okay? Wolfgang, I have 2 questions. The first question is, so you cover our result or not? Because I was not sure whether you have h equal to half inside. No. I don't think so, right?
No, your result is much stronger. So I like that you have your result, Michael, because what we still need is we need a limiting Dirichlet form. Yeah, and actually that's also that the whole procedure that we are doing, you need this limiting point. Otherwise, you have to show much more. And we are happy that you put all of this sweat there and actually show this with this quasi translation invariance, because then we know actually where to go. And yeah, but you need this limiting form. That's very important.
Second question is, when you say Yeah, Watanabe differentiable. Yeah, Watanabe developed a notion of differentiability also in the sense of distributions, like Hida did, and many people did. But you mean really the derivative is an L2, right?
Yeah, I mean really. Yeah, that's how I learned my Watanabe differentiability. Yeah, I mean the derivative is an L2.
Okay.
Exactly.
Thank you.
Thank you.
Anybody else?
Hi, thanks for the nice talk. So I would like to go back to this simulation you did in the beginning about the self-avoiding walk. So in this case of a fractional, so-called fractional self-avoiding walk, does your algorithm in the end indicate how you can simulate these kind of things in the discrete?
So in the discrete sense, we have at the moment another. So we have an off-lattice Markov chain Monte Carlo method to do that. So we did actually standard Metropolis adaptation for the two-dimensional walks. For the discrete case, so we are not working really on lattice. So this one is more like a motivational thing. On lattice, I mean, the good algorithms for this is Polya's earn things. So if you like, you can send me a mail, and then I can look you up these references for you. But I don't have too much knowledge about what to do really on the lattice. So we are doing it off lattice. If you simulate, and with this differential equation, then of course you're also completely off lattice, right? So with this one, we would have just a dt and so on.
Does anybody else have a question? Let me ask the virtual participants.
Okay, so in this case, if there are no more questions and comments, so let us thank the speaker again. And I think we close this